All right, all right. Hello, everyone. How's it going?
Hi.
Can you hear me? Amazing. All right. Well, this is the anticipated, long-awaited STWO workshop. STWO is a pretty big innovation coming to the Starknet ecosystem. It's a next-gen prover built by StarkWare, and it's built on Circle Starks, which was an innovation. There was a paper written about it just last year. So we pushed through the code, and now we have this ZK prover that's available. And the goal of today's workshop is for Maya and to Michael to kind of show you around the super and also to tell you how you can use it yourself. And so it's the name of the workshop is how to use STWO for client-side proving. And so that's a unique feature that it enables. So Maya will go into it a bit deeper today. And just before we start, I'll introduce everyone. So Maya is the product manager at StarkWare for STWO, and then Michael is part of the exploration team at StarkWare, and he's doing some experiments with Nostr and with the Starks, and how to also integrate Starks within the Nostr protocol. So a lot of exciting stuff there. But yeah, without further ado, I'll give the floor to Maya. She has a really neat presentation today for us. And if you have any questions, anything, any curiosities, just drop them into the little chat that we have that we're streaming this on Twitter. And yeah, I'll give you the stage, Maya.
Okay, so thank you. I'll present the slides, and then I was planning on doing a live demo of doing the steps with the slides, but I don't know if the screen share will allow this very elaborate task. So
Let's
let's
go.
see. Okay, so I'm going to be talking about STWO, specifically what we're calling STWO Alpha, which is the alpha release of STWO. STWO is a prover. As you probably know, it's based on the Circle Stark protocol. It proves general Cairo code. We'll show today how to prove Cairo code, how to execute Cairo code. It has we have a few features that were missing in the past in order to have what we call client-side proving, which basically, as it sounds, means that the user can run STWO to generate proofs on the client side, which is useful for many applications. It lets you test your code locally, develop privacy-based applications in which you want to prove a claim and only put the proof on chain and not reveal your inputs or your private data. It's used for gaming, in which you prove some actions that happened on a game, and you only put proof of maybe a lot of state transitions in one proof on chain. And it's good for L3s, as you can prove the state of the L3 chain onto the L2 chain, specifically Starknet in our scenario. STWO will be the main prover used to prove Starknet blocks starting in a couple of months. And yeah, it has a very significant performance improvement over Stone, which is our previous prover. And it also, if you see here from this very small example, we can see that it has state-of-the-art performance over tasks like this is a benchmark for SHA-2, SHA-2 56, and we see that it outperforms both RISC-0 and SP1, even though many optimizations have yet to be included in STWO. So with Cairo code, it beats RISC-0 precompiles and also SP1 precompiles. So we're very excited to present it. So the goal of the workshop is to actually hands-on learn how to generate Cairo code, execute it, get the execution files, the trace files needed to prove, be able to explore them if we want, then use them for proving. We'll see some examples, and hopefully we'll have time for questions. Disclaimers about STWO. STWO is a work in progress. It's not yet sound. It will be sound in a few weeks, and we will remove the disclaimers from the repo as soon as this happens. But for now, it's mainly used for benchmarking and for playing around with, getting used to by developers. And there may be some breaking changes due to the fact that it's a work in progress. Performance will improve. So the performance you're seeing now is expected to improve by at least a factor of 2 within the coming weeks to months. The bootloader I'm going to skip because I don't know if it's relevant for this setting. The verifier is still unstable. So we have a verify command that we'll see, but don't count it quite yet. Hopefully within the next couple of weeks it will be stable enough to use. And the Scarb version that I will talk about is still not officially released. So we're using a branch that will be officially released and verified at the end of this month. So the thing that you will have to do in order to prove Cairo code with STWO is first to install Scarb, which is a Cairo package manager. And this is a standard way to write Cairo code. And I've included so typically you do this via ASDF, and you can verify that you have the correct version to run by also using ASDF Global. And we're going to use the latest nightly version for this demo. I'm not going to do the installation now because I don't want to bore you, but this is what you should be using now, and we'll update the README in the repository when you need to use a different version, so please follow up with this. And so the first thing you would do is to create a new project, and you use the command scarb new and the name of your project, or package is a better name. And then you need to go to your cargo, to the Scarb toml file and make some changes. So I think I want to do this live. So let's see if I manage to share my my screen. Okay. I have to change my system preferences.
I think she's coming back in a bit.
Hear me?
Hello, yeah, you're back.
My browser decided to not cooperate. Okay, let's try sharing my screen again. Okay. Okay, so we are now creating a new project. So let's create a new Scarb project with Scarb new Maya test demo. I'm sorry, I'm looking the other way. I have two screens. And we're going to do a Cairo test, not a Starknet Foundry, because we are going to test locally, not deploy smart contract on chain. And that's it. We have our new project. And so now what we want to be doing is we want to go and start modifying the files that we were talking about. So we'll go to look at our files. And now you can see that under Maya test demo, let's close all of this. We have a Scarb toml file, and we need to modify it according to what we had in the presentation. So let's do that now. Let's see if I can share maybe my entire screen. It should be easier. Okay. Screen one. Okay. Oh, but then I need to move my. Okay. Let's see if this works.
Yep. You see.
So yeah, you see. Do you see also the browser though?
Yeah.
So we're supposed to add the target executable to our file here. And we want to add under dependency our Cairo execute version. So since I'm using the nightly version, I'm going to be using the not 2.9.2, but once you have a stable version of 2.10, then this is what you'll be using. And also we'll add a Cairo tag and we'll put enable gas false. And this is just because we're not doing anything on Starknet. We're just testing locally, so that we don't want this flag to be in the way. This gas. Okay. And we should be all set. So we're going to save this and let's follow up in the next step of our instruction list. So we have an example here of what our Scarb TOML should look like, and and we have everything, if I'm not mistaken. And so the third step would be to write some Cairo code. So we're going to do something very minimal in this example. We're going to take this function that takes an input, some integer, and returns it. So very simple example. And so within our package, our code, we're going to go to source, and we have a libcairo file. And whenever we generate a Scarb project, we already get this by default. So the default code would be a Fibonacci example. So let's get rid of that and put our function here. And we are adding this executable here, which will symbolize to the STWO prover, when we get to it, that this is what it's supposed to prove, the execution of this function. So we're going to have this exactly once in our file, and you should put this typically over your main, and this is what STWO is supposed to look at to prove. Okay, so let's save this, and now we can continue with our instructions, and we look into executing our program. So you execute your program with a new command that didn't exist prior, called Scarb execute, and you give it your package name, -p your package name, and you have some additional flags like arguments, which we will use in order to give, because if we recall, our function takes an input. So we're going to give it an input using the arguments option, and we're going to also print our outputs just so we know that we're not cheating. So let's do that here in our nice terminal. Okay, so let's use our Scarb execute command. I hope you can see what I'm doing. So as you can see, we use Scarb execute -p my package name, and then we're going to print the output. And but first, you know what we're going to do? We're going to go to our correct repository, and then we're going to do this. And you can see that my program is compiling and it finished successfully. So this 0 means that the program exited as expected. A 1 would mean something bad happened, but the 0 means everything is good. And the output is 5, because if we recall, then our code was just supposed to return our input. So we gave it as input 5. This is what we ran, minus arguments 5. And we got the output 5, so this is as expected. And we can also see that it's telling us that the output is saved to target execute my test demo execution 1. And this 1 is important. Why is it important? Because I can now run my program again, execute it again with input 4, and it will likely finish successfully, I hope, with printing 4. And now it's saved under execution 2. So now I can go ahead and prove either one of these executions if I want. I just need to give it the correct execution ID. So let's go back to our slides. So for proving, again, we'll use the new Scarb prove command. So this is also a previously non-existent command. And we'll give the execution ID, and it should hopefully prove our program. So let's do that. Okay, so, and I'm going to do this on execution ID 1. And it's running and proving, and it said, and it succeeded, and we have the proof saved in this path. So now we can go to, we could go and look at our proof if we want to, and we can also verify our proof in the same way that we proved it using the Scarb verify command. So verifying the same execution ID says that it's verified successfully, and I can try to give it a different execution ID and it should fail because there's no proof there. So it says no proof file, but also it should fail on non-valid proofs. Okay, so this is basically how you would go ahead and use Scarb to prove. There is another option if we want to prove not using Scarb. So we can execute our program with Scarb, and we can also prove in a standalone mode. So this would mean that you clone this STWO Cairo repository to your local environment, and you have to build and run the prover, and then you can prove the program using the artifacts that you got from your original execution. So if I go back to my execution, I can see that when I executed, my files were saved to target execute Maya test demo. So let's look what we have there. Target execute Maya test demo, and we have two executions. So let's look at execution 1, and we have all of these files: airprev, airpub, and memory, and eventually the proof because we generated the proof. But if we hadn't, we wouldn't have this. And these are all files necessary for the prover. So once we generate these files, we can also go ahead and prove using this this standalone. So if you want to do that, and the reason you would want to do that is because you get some more information about your proof. So if we do this, so this, we can go to Cairo, and I think STWO Cairo prover. Yeah. And we can hopefully just run this on my, so I need to get my correct path. So this would be, no, I need my complete path. Okay, let's do this. Am I not seeing this? Oh, okay. CDN Maya test demo. Okay, so this is what we want. So let's go back to, yeah. And now our path would be and then my test demo, and then all of this. And let's copy this. Here. And let's put the proof also here. But let's call it proof Maya, just so we know it's different. And then we should be able to run it. And Yeah. Oh, I failed because I did something. Okay, let's do it on an example that I had prepared in advance, just not to bore you too much. Okay, so here if I go to, I have a SHA example ready here. It's called Maya SHA 256, and I run it, and I can run it using my command. And you know what? I find this boring. You can do it at home. Let's go to Michael's example, and he can show you how to run it whichever way you want to.
Sounds good. Amazing.
Yeah.
I have a couple of questions, but I think we can go to those right after Michael's presentation.
Yeah.
So, Michael, can you share your screen?
Yeah. Sure. Yeah. Thanks so much, Maya. Great demo. So I will. Yeah. Just like
We're
follow
hearing
up.
there's a bit
Sorry.
of a you have a bit of a weird
Like echo or some. Sorry. Like what?
yeah, weird audio.
You have an echo.
Oh, I see. I see. Okay. Let me like see if I can do something with it. So like share my screen meanwhile.
Right. So, yeah, let me like address like one question while we're like still here. So regarding the entry point. So good question. So like unlike Rust, where you have kind of like a convention that's like you have like a main RS file where your like main entry point is. So in Cairo, we have like a more like loose convention. So you can have your entry point like in any file. You just like have to mark it with this like executable attribute. So moreover, in the future, you'll be able to also have multiple entry points, and they'll be able to specify which entry point exactly you wanted to use to run your code. All right, so we're like moving next to another example, and like generally, so I'm super excited about like Find Simple like for two reasons. So first, it's finally so it's feasible to prove like a meaningful problem, like program on your like on consumer device on your laptop, and this is like super cool because like before with our previous prover, it was possible, but it would take you like minutes. So now it's seconds or even less. And secondly, so we used to think that Cairo, I mean, like many people like used to think like, hey, Cairo is the like a program for smart contracts on Starknet, whereas it's actually like a generic purpose language like Rust, which you can use to write basically anything, like whatever. But it has like a superpowers that you can prove it, and you can prove it like really, really efficiently. And here, so I wanted today to share with you one of the exploration projects we're working on, where we try to apply Starks to do something useful. And this time is going to be about Nostr. So for if you don't know like what Nostr is, so at its core, but first of all, so Nostr stands for nodes and other stuff transmitted by relays. And at its core, it is the very simple yet super powerful message transport protocol. In that protocol, so users send messages, which are also called like events, to like nodes, relays, which are then rebroadcast those events in the network. And every event has to be signed. So every user is associated with the key pair, which is like, by the way, compatible with Bitcoin. Uses like additional like superpowers, but it's kind of like topic for another discussion. And yeah, therefore, so like every event is signed cryptographically using Schnorr scheme, and upon like receival of like any event, you have to validate that it's can be like parsed, that you can deserialize it, that like hashes like match the content, and finally that the signature is like valid. Uh, so that here's like roughly like the how protocol works. Now, what you can build on top of it? You can build like many interesting things. So the most uh, like broadly known thing, and it's what Nostr is associated like with, is the social media app. So you like heard that Nostr is a like decentralized media protocol, and you can think of it as the as X, like Twitter, but censorship resistant, and also kind of like self custody. So like users own their like posts, like replies, comments, like everything. So it's like pretty cool concept. And Nostr, like so far, Nostr like hasn't get like significant traction yet. So there is like an activity. Like hopefully, like this year is going to be like pivotal in its life, and we will like, see like more and more adoption and like use cases, and more like also like apps built on top of Nostr. But yeah, circling back like to Starks, like how we can use Starks to improve this protocol, right? So as I mentioned, if you wanted to like verify, like validate like any Nostr event, you have to verify signature. And this is like pretty non-expensive operation. Although if you have like a significantly large amount of signatures, like think like thousands of like tens of like thousands like messages, posts and replies and likes and like everything. So it can become like a problem. So it can be like become like a bottleneck. Consider like a use case where let's say you wanted to create an archive of like all the posts, like all the activity of yours, or like all the activity of some like segment of users, or let's say uh, all the posts like relevant to like some specific topic. Just like a example that relates. Maybe you want to use it as a training data for your AI model or like anything else, right? So here you are. You have like a huge amount of data or like events, and you need like somehow to verify the integrity. So you need like to check that those are like actually Nostr posts, Nostr messages, like Nostr replies, like etc. Right? So like a straightforward way to do that is just like go like one by one and like verify like everything, like content, like signatures, like everything, right? So that's like a huge like chunk of work, right? And in reality, right? So you would just like trust like whatever like the closest relay could get you, right? Same way as we trust RPC responses like in crypto, right? So it's like all over the place. So that's not good, right? Because like you somehow like trade uh, like decentralization for like high throughput, like efficiency, like whatever. How can it be fixed? So cool like property of like succinct proofs, right? So, like validity proofs is that you can compress like a large amount of work, right? So that the you don't have like to do this like every time, right? You do this once, compute a succinct proof, and then the verification will like remain like more or less like constant and like very like it's going to be like a very fast process. So here's the idea, right? So we have like a huge like amount of Nostr events. We wanted to compress them, like to compress the verification of the signatures, so that like later, like in later stages, if we wanted to, let's say, like import all those events or like do something with this data, we can like verify the integrity, just checking like a single proof. Okay, so that's kind of like the what we wanted to solve here. Uh, so Now let's switch to the code. So what are we doing here? So we're using Cairo first to implement signature verification, and in the yeah, so in this project, it's pretty simple. It's just the implementation of the hash function, because you need to generate fixed size digest out of your data. We have implementation of the Schnorr signature scheme. It's based on Garaga, by the way. Garaga is amazing. We also have some Nostr specific things, like how exactly you compute the hash challenge, et cetera, et cetera. And finally, it's just an entry point, right? So same as Maya showed you, right? Annotated with the attributes that accepts a list of Nostr data. It's not exactly like a Nostr event. It's just the parts that we need. And the body of the program is the loop where we verify the events, the signature of those events one by one. Okay, pretty simple. So right, so few things that you should know. As Maya mentioned, right? So there are few new commands introduced to Scarb. First, it is Scarb execute. As you may remember, so before we did have some command that could run your arbitrary Cairo codes, though it's not a smart contract, and it's Scarb Cairo run. It is still there. It is deprecated, and we will removed, and we will just leave with execute uh, after that. So the difference between Scarb Cairo run and Scarb execute, from the developer standpoint, is first, the arguments are formatted in a different way. So before, you may remember that you had to pass a nested array of field elements, right? And the you could provide that with a file, and the file would look like this. So in Scarb execute, it's slightly different. So now it's just a flat array of also field elements, but they are now strings. So it's small difference, but it can be annoying. So why the array is flat? Is because now your entry point is actually wrapped. So and it's actually pretty convenient, because before, for instance, we had a limitation for the main entry point type, right? And it should be exactly one argument of the this specific type. So now this limitation is lifted, so you can have an arbitrary number of arguments of various types, as long as they can be serialized, deserialized. And what Cairo does under the hood is wrapping your main function with a wrapper function that accepts exactly that has exactly this signature. In fact, it has one extra argument, but that's not important here. And it does deserialization for you as the first step. Okay, so it's important to understand, because it might be tricky when you try to pass some arguments to your function, right? So once again, you have to pass to the Scarb execute and a flat array of field elements that would deserialize to whatever the structure of the arguments of your actual entry point. Okay, so once you do that, so you're good. It's the same workflow. And so here, what I have here is I have a bunch of scripts that help me to first generate Nostr events. So this is how they look. So they have some identifier and the public key of the user that signed them, and some metadata, the content, and the signature. Okay. So I have a script also that helps me to convert these high level like human readable data to the format that is understandable by Scarb execute, right? And it's just like a flat list of field elements, right? So then here I just like have several helper scripts to kind of execute the pipeline, but basically it's just what you do is you just call Scarb execute. I'm using custom profile with some flags, but it's not that important. And there is an extra flag that allows you to pass the data for the arguments. All right. So similar to Scarb Cairo run, right? So maybe you don't want to recompile your program every time. So there is a flag that allows you to skip that and just do the execution. So again, second important thing about Scarb execute is before you may remember that the output of the compilation was CR file, right? So CR is the intermediate representation of your Cairo program, and it's not it's final form, right? So you in order to run the program, you also need to compile Sierra down to custom, and then you can execute the assembly in the virtual machine. So now we have a different output format that is called executable, and this is closer to a common executable that we have in Linux, in macOS, and other machines binary files. So and you can see that now we have actual bytecode here. So this is this file is contains everything that is necessary to run your program, right? So this is a second big difference. So once we have this executable, we can prove it. So okay, one important note is you can execute in two modes. So the default mode is called standalone, and there's also a bootloader mode. So the difference is in a standalone mode, it's your program is what is going to be proved exactly, and in a bootloader mode, your program will be wrapped with another program. So it's closer to how it happens with Starknet when your smart contract is actually plugged into a larger program, which is Starknet operating system. Okay, but we will just play with standalone mode, and this is what you would likely use for just playing with two new Scarb execute. So once we have the executable, we can execute it. Okay, and the result of the execution, right, as Maya already showed to you, is 4 files. So this is the exact files that you would get earlier by using Cairo one run from Lambda class repo, in case you already had experience with that. And in fact, it's also compatible with Stone. So if you want to prove this with previous Sprue version, so you'll also find it to do that. So once you have that, right, we can just call Scarb just Scarb proof and program a common summary. Yes. And it will do the trick. So notice that you can actually do everything in one command. So you can, if you do Scarb proof -- execute, that would build your program, execute your program, and also prove it. So it's kind of like, yeah, all steps like in one comment. And yeah, so everything is fine. So the proof is like written to the output. And yeah, so what we just did is we created like a bunch of Nostr events. Okay, so we encoded like the data for Scarb execute. We executed like the program which verifies those signatures, and like finally we prove that the verification, like the execution was correct, right? So what this proof means is it guarantees that if you take like those events and like compute their like hashes and compare like with the data that is in the output of the proof, it would mean that all those events have correct signatures and you don't have like to spend time like verifying them. So once we are able to scale that to like tens, like hundreds of thousands of like events, so it will become like feasible, like like it will make sense like economically and also like in terms of like optimization to use this mechanism. But it's like again, so it's not like the only thing we can do like within Nostr ecosystem, like Bitcoin ecosystem with Starks. And we're like continuing like to exploring like other like use cases. And yeah, we're like super excited, super optimistic about the potential of like Starks for scaling, for like removing trust, for even for privacy, like at some point. So yeah, this year is going to be awesome. Thank you so much for watching. If you have like any questions, so please reach out to us, like using like any channel. Also, yeah, star like reposting like keep Starknet strange, and also stars cares too. So this is like very important for us. And yeah, thank you.
Amazing, amazing.
Thank you. Thank you.
We have a couple of questions that we could go through. So first for Nostr, like what's the next objectives to really find an integration for Starks in the Nostr protocol and eventually like bring Starks to all these, I guess, clients that use Nostr?
Right. So for us, like the next big step is to as I like, right, to be able to process like a large number of data, and for that, so we need like really efficient recursion, and this is going to be like one of the killer feature of like STWO, like with Cairo, like in particular. So we were able to do like just insanely efficient recursion, and like like handle really like large jobs in parallel, in particular. And so once like it's done and we will have like a proof of concept that this works and this is actually useful, so we'll also try to do like a MVP with like one of the Nostr events. So since like Nostr is like a decentralized media protocol, there are like multiple clients for it. So yeah, we'll like probably like take like one of those and create like a fork like with a specific like mechanism. So we'll also yeah, we're like in contact with like developers from the ecosystem, and we're like trying like to validate our ideas, and also like we're asking them about like use cases that they see where like Starks can be like of good use. So we'll like try to find like a good like intersection between like two ecosystems, and where we can have the you know like we can have like the most out of it, get the most.
Amazing. That sounds like super exciting. Like for me in my case, I cannot wait for it. It's always nice to see like where you could put Starks in which protocol. But like now coming back to also you, Maya, and also you, Michael. So as of now, Starknet operates with Stone. So Stone is the current Stark prover that is being used, and STWO is so the next generation prover. what are the differences between the two, and what does STWO bring to the table?
Okay, so there's many differences between Stone and STWO, but I think from the point of view of users, the main difference is that since STWO is a newer technology using circle starks, it works over a smaller field, which makes it highly efficient compared to Stone. STWO is also optimized for proving, whereas Stone was optimized for verifying. So Stone is very cheap to verify the proofs, and that's very useful for when you want to, for instance, settle Starknet on Ethereum. So, and this is because of the inherent design of Stone versus STWO. So, STWO optimizes, Stone optimizes for fewer columns over many rows in the trace, if that means anything to anyone listening. Whereas STWO, each component would be as few rows as possible, preferably one, which makes the proving time very fast, at some expense of the verification time. But since STWO is so much faster than Stone, then even the verifier is efficient. So just the STWO is superior technology. Stone is also an amazing prover, and it was the first to do what it does, which is prove general code in a very efficient way, and it's been doing a fantastic work at proving Starknet blocks. But STWO is really the next generation, and there is still a long ways to go in terms of optimizing STWO even further. Currently, Cairo is a language that works over the large field that is compatible with Stone. So there's a lot of optimization to gain by making adjustments for Cairo to operate even over the smaller field, the M31, which is compatible with Stone, with the STWO. So I think that's probably the main difference that derives the performance. There's also many other engineering efforts that were done on STWO versus Stone. So there's each opcode would be separate. There's no need for layouts. If anyone has been messing around with Stone, you know that there are layouts in Stone. So in STWO, there is no need for layouts anymore. And this also means that you don't have to pay for padding to the nearest whole power of 2, which actually can further optimize your program. So there's a lot of other optimizations that have been done in STWO versus Stone.
Yeah. Okay. And now I'm thinking of a general use case that's easy to understand. Let's say that I want to start prove a passport, for instance. From a user's perspective, like what's the speed on that? Like how is it 1 second? Is it 10 seconds? Is it more? Is it less? What's the performance overview over these types of use cases?
So I'm assuming that to prove a passport, this is not a completely well-defined operation because it depends on the details. But it would probably mostly either involve hashes, which is a very good use case for STWO. So I would say probably in the second to milliseconds, hopefully for that. For more complex operations, probably not more than a couple of seconds, but also it really depends on your implementation. But we're aiming for reasonably sized programs to reasonable code to be able to run very fast on client-side apps or devices.
Nice. And also thinking of broader use cases such as, so you can obviously run, and we will run STWO on the Starknet rollup, but also thinking of AI or just verifiability in general, like where do you see STWO fit in these different use cases, and what can it enable for these types of projects?
So STWO, so AI is, I think, a great example of applications where things are easily broken into chunks that fit into a recursive flow. So when you think of a neural network, you can break up your graph into smaller components and compute things for each component. You can break down the dependency flow of your graph according to operations. You can have a predefined error for each one of these components. If you would like, you can invest in developing errors for this type of operation. So this really fits into anything, to a scenario where fast recursion is everything. So I don't know if, like, I'm thinking not to train your model, but definitely to run your model if it's I think it would be state of the art to use for this type of thing.
Okay, nice.
What, by the way, sorry. So this is like exactly what the Giza team, like Raphael from Giza team, is doing. So it's already like
very true.
in progress. So
Yeah.
super excited about it.
Yeah, that's with the haiku. Do you actually have a couple of words that you want to say on that front? Just in terms of how they're using STWO or yeah.
Okay, yeah, sure. Yeah, I mean, so I'm to be honest, I'm also like very like excited about like the work Giza is doing on that front. So I expect it to be like super like performance like compared to other CPML frameworks. Other than like in ML, so for the client side, as you mentioned, right? So ZK password and like everything, like ZKML, like in the like similar like technology. So that would be like a great enabler, and especially because so you can already use STWO in like in the browser. You can run it as like in WebAssembly, and there was a really cool demo done by Bartolome from Herodotus. So it's like working. So there's like some room for improvement in terms of the performance. But yeah, still, so you can already like play with that in the browser. So that's super cool. We are, so as I mentioned, right? So we do like a bunch of exploration projects in the Bitcoin ecosystem. So we are working on the like full consensus client for Bitcoin, where we can use, where we plan to use like STWO to like recursively verify like the entire Bitcoin chain. So we try to apply Starks to Nostr, to also to Cashew protocol, and like in a couple of like other projects. So it seems to be like really powerful like primitive that we can use to like scale like computation. And yeah, like in terms of like privacy, so like so far, right? So there was sort of like a dilemma, right? So you want like privacy, you go to like elliptic curve like based snarks. If you like for scaling, so you use like Starks. So we will have like a certain like notion of privacy, like an ultimately like a like statistical like privacy like at some point, so that you don't have to like sacrifice like any of that. So you can have like scalability like in privacy, like in one technology stack.
Yeah, and also we are heavily looking into fully ZK-fying STWO within the upcoming year. So look out for that. So it's an ongoing project to make STWO fully ZK. And also, I would maybe like to add a use case of anything that has to do with integrating trusted hardware and Stark. So, especially in the machine learning world, you can run a model on a trusted device and generate an attestation, and then use Starks to further prove or aggregate this information onwards and propagate it to anywhere it needs to go, both for privacy and for provability. Yeah.
Also, like for this case, I almost forgot, and this is like one of the coolest things. So like I mentioned that we wanted to prove like Bitcoin chain with Starks, but we can also prove Ethereum, and that's like what's like Kakarot guys are working on, and they're like already like doing like amazing progress with like using STWO to prove Ethereum blocks. And yeah, they like target for like real-time proving this year, and I think so they will get there like for sure. So this is super exciting.
Amazing. And we're still in STWO alpha, but where would you point devs to go have a look and go start with playing around with STWO and potentially integrating it?
So definitely the STWO Cairo repository has everything you need. It will have the README updated hopefully today. It was already approved and it should be merged today. You can, of course, I can share my slides as well. But the README should have everything and will be maintained and updated. And you can use it. And if you don't see the README there now, then I will share the branch for the pull request until it at least is merged. If I can share it here. Can I share something?
Just send me the link and I'll put it on the screen.
I'll send it to you. Okay. Cool. Yeah.
Amazing.
Great.
All right. Well, we're right on 1 hour. This was a really interesting workshop, and also the first of many STWO workshops, I hope. And this is just the beginning. But things are moving fast, and there's a lot of exciting stuff coming from StarkWare side when it comes to Starks, and also, well, this specifically use case, so STWO. And if you have any questions, well, the Discord is open to join, and then we also have a bunch of Telegram channels. If you go under Starknet.io, and I'll put the link on in a sec on the screen, but you can find all the relevant online communities to reach out to. So yeah, whether that's in Portuguese, English, and Chinese, we have a lot of communities. And then we have also Starknet AI that is specifically tailored for AI discussions within the field of Starknet. And yeah, we're also on Twitter, we're everywhere. Just comment and we'll go help you. And we're everywhere on Telegram. So if you have a question, just send a message however you want, and we'll be there to help you. So yeah, this marks the end of the workshop, and I want to thank you, Michael and Maya, as well, for joining and explaining how STWO works and how to do a bunch of client-side proving. And I'll see you in the next workshop.
Thank you.
Thank
you guys.
Bye-bye.
Bye-bye.